Hello, welcome to another Key Comp Eng video. This one is the amplifier and analog to digital converter integrated circuit design project, which my lab partner and I completed in December of 2025. The goal of this video is to do a quick overview of the presentation and not get too lost in transistor level theory and circuit design, merely to demonstrate the project and promote further conversations about it. The premise of the project was that it was a smartwatch application where you were to design an IC for a analog multiplexer, a programmable gain amplifier with 4 settings, and a analog to digital converter. The first slide of the presentation summarizes the performance of the analog multiplexer, which has 4 inputs switched with a 2-bit binary signal seen in the bottom. You can see the blue line is showing the output of the multiplexer, while the other dotted lines show the generated signals that are being switched between. So you can follow the blue line through the highest amplitude signal, and when the next bit switches to 1, you can see the signal changing at each binary increment, with the last one being connected to 0 volts. The multiplexer was designed very simply using transfer gates consisting of both N and PMOS of the smallest manufacturable size for the process, which was a TSMC 65 nanometer process. The smallest size gives you area efficiency and also prevents extra capacitance from building up. So a transfer gate, because it consists of N and PMOS, you need inverters on your signal lines to switch both the N and PMOS. The next component was the programmable gain amplifier, and the results are summarized in this graph. So you can see the orange line is the generated signal input. The vertical lines represent where the digital switching is taking place to change gain levels, and the green line represents the output at gain of 1, 2, 3, and 4. This slide details the schematic of the op-amp, which is made in 2 stages. There's a current mirror on the left connecting all the 2 stages, and then in the center is the differential amplifier, and on the right is a common source amplifier. These were designed at the transistor level, so the dimensions, like the length and width and the number of fingers on each one, were all things we were able to adjust in our pursuit of getting the correct component. And it was very important to get this component right because it's the core of the amplifier, and it was also used as a comparator for the analog to digital converter. The op-amp was specified to achieve at least a gain of 500 times. So we went a little bit above and beyond, and as you can see, from left to right, we have a transient response where, with a input signal centered at 0.5 volts and varying by, I believe it was only 20 millivolts, we get saturation of our, it was a 65 nanometer TSMC process, so with 500 times gain, you very quickly run out of bus voltage, so you hit saturation very quickly, which allowed us to use the op-amp as a comparator. And you can see on the far right that it is centered at 0.5. The ADC was the most elaborate part because it also utilized some Verilog A code to monitor and produce digits. So I chose to do a charge distribution analog digital converter, and what happens in this design is you take a sample and then you do comparison with your with how much charge is built up, and you index through your different bits, which are actually capacitors, and then compare if your charge is greater or lesser than those, and then that's how you go from an analog to digital in our design. So this slide details the performance of the analog digital converter and details the sequence of a conversion. So the specification was that we be able to convert at 100 kilohertz, and in order to do that, I used a clock at 1 megahertz, and that is because there is a process to running a conversion for the system, which was six bits. So as we're doing conversion, we take a sample, and then there's a hold period just to make sure everything is stable, and then there is a switch, this fifth switch, so the most significant bit, this is the one with the most capacitance, is switched, and then you compare the two sides of your comparator between the amount of charge at your sample and charge at switch 5, and if you have more charge than is accumulated at that switch, you keep it on and try the next one. If you don't, you leave it off and you try the next one. So because the code is written in Verilog A, the process of doing a comparison just doesn't quite happen happens kind of instantaneously. So you're doing a switch and then you're comparing for the one before and then switching immediately afterward. And then you continue to do that. So you come down, you do the switch, do the comparison, switch, compare through all your bits until you get to the last stage and you write your output, and then you take another sample. So the operating range, I ended up tightening from, instead of being between 0 and 1 volt, we knew that our signal was going to be between 0.375 volts and 0.625. So by tightening the range, we got more resolution per bit. So we achieved a resolution of 3.9 millivolts per bit. We had a lot of difficulty getting it perfectly linear, but that's the name of the analog design game, it seems. This screenshot depicts the full conversion going from the bottom range, which was identified. This was during development, so I hadn't quite tightened the window perfectly. So I realized I should move up my bottom to looks like about 0.45, but I hadn't quite gotten to the point of realizing I could tune in the top. But you can see, even though it's a little blurry, it's a little small, but you can see the digits indexing all the way through the whole conversion. So that was when I knew my design was successful, and we pursued a tighter window. It's a very the graph really shows you the whole process of converting and how the comparison switches from finding the most significant bit to be needing to be held on to, then it becomes a negative comparison as you get to past the midpoint. The end goal is to have the top level implementation where we have a set of inputs go through our analog multiplexer into our programmable gain amplifier, and then through the analog digital conversion. Here is the presentation setup to demonstrate the complete implementation of all the components. It had to be limited to fitting on a PowerPoint slide, so the goal was to show every feature, every component working. So in order to do that, I came up with this setup where the red line shows the input signal. The input signals were fixed at 500 millivolts, 480, and 520, so that it was very simple to understand, and that was the range of the analogs of the waveform, like a sinusoidal signal that would be coming in. So we knew it was going to have an amplitude of 20 and centered on 500. So to keep things simple, each one is just a flat line, and then you're able to, in the digital readout, see the multiplexer switching between the center, the bottom, the top, and then 0. You're able to see the gain level. So for this side, and I chose to split it up so each gain level is its own slide, and that way you can see the same set up for each gain level. So I'll switch the slides in a sec, and then the binary output of the whole conversion is shown at the very bottom. So if I skip these ahead, you can watch the blue line getting farther and farther from the input signal as the gain increases. So documenting the results along the way, on the least amount of gain of 1, we were able to get distance of 5 digits between the lowest reading and the highest reading, and then when you increase the gain to 2, you get around twice as much. So there's just some data of some conversion measurements that were taken, and they're switched from millivolts to a binary signal in 6-bit to a decimal equivalent. And as you move up, we notice that the conversion gets more linear in the higher range, and it's very challenging to get it to be linear near the bottom. But we proposed some solutions to overcome that problem, such as moving the signal from the gain amp up within the range that the ADC is measuring, or we could potentially adjust the capacitors used in the ADC to make them a little bit smaller, which would also help improve linearity toward the bottom of the conversion range. So thank you for your interest in this quick video of the IC design project.